Dear student, I once again welcome you to the online class in which operational amplifier will be discussed. And as in the first lecture, we began from the introduction section to the substructure, and that's why in this class or in this lecture we will discuss or learn rest of the uh, rest part of this chapter, and the topic that we will cover in these lectures are given here. First, we will discuss about the application of OPAMP as integrator, then its application as the differentiator, then logarithmic amplifier. After that, we will learn how an OPAMP can be applied for for voltage to current converter, and then current to voltage converter. After that, how an op-amp can be applied to perform voltage comparator, and then how sinusoidal wave or AC wave can be converted into DC wave, that means half wave rectifier. And at the end of these discussions or this lecture, we'll discuss or learn about the semi-trigger or regenerative comparator. Now come to the first topic, which is the integrator. And in case of integrator, it is an electronic device in which the output voltage is proportional to the integration of the input voltage, and op-amp can be applied to design such an integrator circuit. Here is the basic circuit arrangement is shown, where the input voltage Vi is applied to the inverting input terminal through a resistance R, and the non-inverting input terminal is grounded. And in case of this type of amplifier, the feedback resistance that was used in case of inverting amplifier is replaced by a capacitor having capacitance C as shown in this figure, and the output is V0. Now you know that the input impedance of an ideal op-amp is infinite, and the output impedance is 0. So from this knowledge or this concept, you can easily understand that the point A will act as virtual ground, since no current will be passing through this op-amp. And then also you understand from this figure that the current that will be passing through the resistance R will be that current which will be flowing through the capacitor. That means the current, if the current passing through the resistance R is I, and that passing through the capacitor C is I prime, then this I and I prime will be equal. And also we can realize this from the concept of Kirchhoff's current law, because this current is entering at this point and this current is leaving at from this point. So the algebraic sum of these two currents will be 0. That means I plus or minus I prime is equal to 0. So I is equal to I prime, it is very clear. Now let us calculate the value of this current I, and this current I can be found out from the potential difference this point and this point divided by the resistance R. So I is nothing but Vi. I is nothing but Vi minus 0, as it is a virtual ground. So Vi minus 0 by R1, that is equal to Vi by R, or Vi by R. Now let us concentrate on the current I prime, and this I prime current is nothing but the change of or the rate of charge that will accumulate in the capacitor plates, and let dq is the charge accumulate on the capacitor plates, and the time required is dt. So this I prime will be the time rate of change of the charge accumulation. That means C will be that means I here I prime is current flowing through C, that is equal to dq by dt. Now the charge that will accumulate on the capacitor plates is nothing but the product of the capacitance of this capacitor and the voltage difference between these two plates, the product of the capacitance C and the potential difference between these two plates, and well, that is nothing but and that can be calculated here, that U is equal to C, and the voltage difference between these two plates is nothing but, here it is the potential is 0 and here the potential is equal to V0. So as we consider that the current is flowing in this direction, so the potential difference should be 0 minus V0. So here you can write Q is equal to C into 0 minus V0. That means Q is equal to minus CV0. Now I prime is equal can be calculated from this relation. So I prime is equal to dq by dt. That means it is equal to minus C into dv0 by dt. And also you know that this I prime is equal to I, that is nothing but vi by r. So minus C dv0 by dt is equal to vi by r, or from this relation you can write dv0 is equal to vi dt into minus 1 by cr, or v0 is equal to minus 1 by cr integration vi dt plus k where k, plus k where k is a constant of constant and whose value can be calculated from the initial condition, and the initial condition can be realized in the in such a way that when the time is considered to be 0, then no current will be no charge will be accumulated on the capacitor plates. So in that case, the current in this sense, K should be 0. K should be 0, or in and then we can write B0 is equal to minus 1 by CR integration VI dt. That means the output voltage is proportional to the integration of the input voltage, and in such way an op-amp can perform or an op-amp can be used as an integrator amplifier. So, and in this case the amplification is 1 by CR, the gain is nothing but 1 by CR. And since in this case the output voltage is the integration of the input voltage, so if you use input voltage as a sine wave, then the output voltage will be cosine wave or vice versa. Or if the input voltage, if you take the input voltage as a square wave, then the output will be triangular wave or vice versa. So it is very interesting. Now one point should be discussed in this case, that as you have used a capacitor in the feedback in place of feedback resistance, so the reactance of this capacitor, how much will be the reactance of this capacitor? Here is the reactance of this capacitor xc, that is equal to 1 by j omega c. Now if you use a DC voltage in the input terminal, then what would be the value of the capacitive reactance? That will be 1 by j omega c, that is equal to 1 by 0, because the omega for DC is 0. So that is equal to infinity. So if you use a DC source, then in the input terminal, then the reactive capacitance will be infinity, and then you can easily calculate the gain of this amplifier, and the gain is nothing but the you know that the gain is the ratio of the feedback resistance to the input resistance. Here you will get the capacitive reactance, which is xc, and here the input resistance R. So the gain would be xc by R, and since x is infinity, so the gain will be infinity. That means any small value of the input voltage will saturate the output voltage. That is, if you apply a small input voltage, then the output voltage will saturate to the saturation voltage, and this is obviously a problem. And to remove this difficulty or to decrease this problem, our resistance here, see here, a resistance R1 is connected parallel with the capacitor, and when R1 is connected in parallel with this capacitor, then the net resistance of this combination will decrease, and in this way the gain can be reduced from that was in the previous case. So if you use R1 in parallel with the capacitor, then the resultant gain will be decreased, and in that case, whenever Vi and in that case the output will not saturate for certain values of input voltage Vi, and the value of R1 should be in such the value of R should be chosen in such a way that the time constants of the C and R, that is CR1, and this time constant must be large compared to the period of the input voltage. And further, also to remove the error that was arised due to the presence of the capacitor of this capacitor, that means the very high gain of the amplifier, you can also use another resistance R2 in such a way that that the value of R2 should be equal to that of the equivalent resistance of the parallel combination of R and R1, and these are two and the non-inverting terminal is connected, the one end of the R2 is connected to the non-inverting input terminal, and another end is grounded. So if you use R2 in this pattern or in this way, then the error also can be minimized. So now come to the application of such type of amplifier, and this type of amplifier, that means integrator circuit, are widely used in digital voltmeters. Not only that, they are also routinely applied in case of sweep or ramp generators. What are sweep and ramp generators? They are such type of generators in which the voltage varies linearly with time, and also this type of amplifier is widely used in case of simulation studies in analog computers. Now come to the differentiator, and this there is a similarity between integrator's amplifier and differentiator, that in the circuit of integrator, if this resistance and this capacitor are interchanged, then the integrator will transform to a differentiator. And in this case, you see that here in case of integrator, here was the resistor, and here was the capacitor, and here these two places are interchanged and changed, and in this case capacitor C is used in the inverting input terminal, and R is used as the feedback resistance. And in case of a differentiator, the output voltage is proportional to the differentiation time derivative of the input voltage that is applied in the inverting input terminal, and the non-inverting input terminal is grounded. And you also know that at this point, this is important point A, since the input impedance is infinity for an ideal op-amp, and the output impedance is 0, then you can treat the point A as virtual ground, since no current will be passing through this op-amp. And now, therefore, from our previous knowledge or previous conception, it is very clear to us that the current that will pass through the capacitor, that means I, is will be equal to that passing through the resistance R. So I is equal to I prime. There is no doubt about it. Now, to find out the value of I, we concentrate in this region, and in this region that we also calculated the current that will pass through a capacitor is nothing but the time rate of change of the charge that will accumulate on the capacitor plates, and that means I will be dq by dt, where dq is the charge accumulated on the capacitor plates in time dt, and Q can be calculated as Q is equal to the capacitance of this capacitor into the voltage difference between these two plates. And since it is zero, the potential at this point is zero, and this is the input applied voltage Vi, so here Q can be written as C into Vi minus 0, that means C into Vi. So I can be calculated from this relation that I is equal to C into dVi by dt, and writing is as equation 1. And further I prime can be calculated from this portion of this circuit, that I prime is equal to the potential difference between these and these, so 0 minus V0 by R. Here it is written here I prime is equal to 0 minus V0 by R, that is equal to minus V0 by R. So since I prime and I are equal, so you write from these two relations that minus V0 by R is equal to C into dVi by dt, or V0 is equal to minus CR dVi by dt. So it is clear from this relation that the output voltage is proportional to the time rate of change of the input applied voltage. Here negative sign arises since the input voltage is applied to the inverting input terminal, and the output voltage and the output volt, and in this case the gain is equal to minus CR. Now for example, if you use input voltage as sine wave, then the output voltage will be its derivative, that means it will be a cosine wave, or vice versa. And if you used the input signal or input voltage as square wave, then the output voltage will be triangular wave, or vice versa. So it is also important, and it is very interesting, that the waveform can be changed by using a differentiator, as that was seen in case of integrator. Now point to be discussed in this case here also, and you know that the output voltage is proportional to the time derivative of the input voltage. So if you use sinusoidal voltage V small vi is equal to V0 sine omega t, then the output voltage is here denoted by small v0, that will be the differentiation of this vi. So with a constant multiplication of CR, so you can write here v0 is equal to minus CR, and then differentiation of this is equal to v0 cos omega t with another term omega. So v0 is equal to minus v0 omega CR cos omega t, or from this relation you can write that the output voltage v0 is proportional to omega. That means in case of differentiator, the output voltage is proportional to the frequency of the input applied voltage. Or you can conclude from this knowledge that the differentiator, in case of differentiator, you can convert the input you can obtain the output voltage which is proportional to the frequency of the input voltage. That means the differentiator behaves as a simple frequency to voltage converter, and the magnitude of the output voltage changes linearly with the frequency of the input voltage. Now another difficulty arises in this case also. If the frequency is very high, the input frequency of the input impedance is input voltage is very high, and since the output voltage is proportional to the input frequency of the input voltage, then there will be instability in the output voltage due to the noise in the output voltage, and switching spikes will be there will be switching spikes in the output. So there will be so the output will be unstable, and to avoid this difficulty, another resistor which is denoted by R1 is connected in series with the capacitor C, and the value of R1 is taken in such a way that its magnitude will be within R by 10 to R by 100. And if you use the value of R1 in between R by 10 to R by 100, then this difficulty or the instability in the output voltage may be minimized. And the resistor R1 limits the high notice here that, or remember here that the resistor R1 limits the high frequency gain and makes the practical differentiator useful only for frequency for those frequency which are well below the limiting frequency, which is given by this relation 1 by 2 by C into R1. And now come to the applications of this type of amplifier, that means differentiator. The differentiator is widely used in wave shaping circuits to detect high frequency components, and it is also used in case of rate of change of detector in the frequency modulation moderators. Now come to the logarithmic amplifier. And what is a logarithmic amplifier? In case of logarithmic amplifier, the output voltage is proportional to the logarithm of the input voltage. That means the output V0 is proportional to the logarithm of the input voltage. And an op-amp can be used in this purpose. And the basic circuit diagram of a logarithmic amplifier is shown here. It is nothing but inverting amplifier, where the feedback resistance is replaced by a simple PN junction diode, and the input is given to the inverting input terminal through the resistance R, and the non-inverting terminal is kept grounded, and the output voltage is measured, you know, that in the terminal number 6. So from this circuit arrangement, and we can see that or we will able to see that the output voltage V0 will be proportional to the logarithm of the input voltage. Now come to the point that the instantaneous current that will pass through the PN junction diode is given by I is equal to, given from the volt ampere characteristics of a given diode, and that can be given as I is equal to Is exponential EVA by eta kt minus 1, where I is the instantaneous current passing through the diode, and I is the reverse saturation current, and then K is the Boltzmann's constant, which has the value 1.3807 into 10 to the power minus 23 joule per Kelvin, and Vf is the voltage across this PN junction diode, and T is the absolute temperature of the diode, and eta is a constant which has the value 1 for the germanium made diodes and 2 for silicon made diodes. Now if we consider that the value exponential EVA by eta kt is much higher than 1, then you can write that I is nearly equal to Is exponential EVA by eta kt, or from this relation I by Is is equal to EVF by eta kt, or taking logarithm in both sides you can write log I by Is is equal to EVA by eta kt, or from this relation Vf is equal to eta kt by E log I by Is, writing its equation number 2. Now remember or notice here that this Vf is nothing but the output voltage, because and you can understand from this figure easily that that Vf is nothing but V0. Now we wish to find out the value of Vf from this figure. Now can look at here. The current that will pass through the resistor R is given by the voltage difference between this and this point, and that is nothing but Vi minus V0, since A is the virtual current, and we several times discussed about the virtual ground, and then thus we can write I is equal to Vi minus 0 by R. That means it is equal to Vi by R. Now substituting the value of I in this equation, so you will get Vf is equal to eta kt by E ln log Vi by Is R, and you know that Vf is nothing but V0, so that is equal to minus V0. Why negative sign is given here, introduced here? Because the input is given to the inverting input terminal. So finally you get B0 is equal to minus eta kt by E log Vi by Is into R. Or from this relation you can easily say that B0 is proportional to the logarithm of the input voltage. So op-amp can be applied in the logarithmic amplifier in this way. Now come to the voltage to current converter. To discuss about the voltage to current converter, let us consider. We think of the case in that the output of a sensor is to be sent to a distant place, and the output voltage of a sensor cannot be sent to a distant place because in that case there will be noise, several noise and power and loss of power when the voltage will be sent to a distant place. But you can send current to a distant place. In that case, so it is required to convert. If you it is possible to convert that voltage into its proportional current, and that current then can be sent to a distant place. So and then the sending of the voltage will be easier, and when the current will be reached to the desired distant place, and if they are that current will be converted into voltage. So the output of the sensor can be sent to a distant place. Now in this case, in the first case, it was required to convert a voltage to its proportional current, and the device which convert a voltage to its equivalent or proportional current is called the voltage to current converter. And an op-amp can be applied to design a voltage to current converter device. Here is the basic diagram or basic circuit arrangement of a converter, a voltage to current converter, in which an op-amp is used. And in this case, the voltage which is to be converted to its equivalent current is applied to the non-inverting terminal of an op-amp, and the inverting input terminal of the op-amp is grounded through a resistance R. And here you notice that the input current which is to be converted into its equivalent or proportional current is applied to the non-inverting input terminal through the same resistance that was used in this case, that is, it is also R. And here also feedback is given, negative feedback is given, and the feedback resistance is R, and the output voltage is connected to load resistance RL through another resistance which has the same value of that of R. And now you know that since the input impedance of the op-amp is very high, that is infinity, and output impedance is very low, so the point A is the point A and the point B will have the same potential, and and if the effective potential that is entering that is given to the non-inverting input terminal is V2, then the potential of the point B A will also be V2. Now now come to the point that if the current flowing through this resistance or the input current is R, then it will not pass through the op-amp because it has very high input impedance, and this current will following in this direction. And if the output voltage delivers a current which will I2, which will pass through the resistance R2, then these two currents will be passing through the load resistance RL, and that's why the load current, that is IL, will be the summation of these two currents I1 and I2. That means IL is equal to I1 plus I2. You can also apply here KCL to realize this relation, because here the current entering in this way, the current entering the point C is I1, and the current is coming towards this point C is I2, and the current leaving this point C is IL. So according to KCL, IL will be the sum of I1 and I2. Now we wish to find out the value of IL in terms of I1 and I2. So first we have to calculate I1. So what is I1? I1 is equal to the current passing through this distance, which is equal to Vi minus V2 by I1. Vi minus V2 by R, which is written here. And also I2 is equal to the current passing through this distance, which is nothing but V0 minus the potential at this point, which is nothing but V2. So V0 minus V2 by R. So IL is equal to I1 plus I2, that is equal to Vi minus V2 by R plus V0 minus V2 by R. So IL is equal to, from this relation, Vi plus V0 minus 2V2 by R. Since the input voltage is applied to the non-inverting input terminal, here you see that the input is applied to the input voltage applied to the non-inverting terminal, and hence the gain of this amplifier will be equal to 1 plus the ratio of the feedback resistance to the input resistance, this input resistance. So here the gain is equal to 1 plus R by R, that is equal to 2. So from this the further you know that the gain is equal to V0 by the input voltage, which is effectively acting on the non-inverting terminal, that is V2. So V0 by V2, that is equal to gain of the amplifier, that will be equal to 2. So V0 by V2 is equal to 2, or V0 is equal to 2V2. Now substituting this value, the value of V0 in this relation IL, we obtain that IL is equal to Vi plus 2V2 minus 2V2 by R, that is equal to Vi by R, or IL is equal to Vi by R. That means IL is proportional to Vi. That means the input voltage Vi can be converted to its proportional proportional load current. So the load current is directly proportional to the applied voltage. In this way, an op-amp can be employed to convert an input voltage to its proportional output current. Now come to the current to voltage converter, as we discussed in this section, that sometimes is required to convert a voltage to its equivalent current, and vice versa, current to its equivalent voltage. And so when a device converts an input current to its equivalent voltage, then it will be called a current to voltage converter, and an op-amp is successfully can be used to design a current to voltage converter, and such a circuit arrangement is shown here. And in case of current to voltage converter, the non-inverting terminal is kept grounded, and the input current, which is to be converted to its equivalent voltage, is directly applied to the inverting input terminal. And here also feedback is negative feedback is applied here through the feedback resistance R, and the output will be V0. So the proportional voltage of the input current will be V0. And since the input impedance of an op-amp is very high, or infinity, so this current will not be passing through the op-amp, and the entire current will be passing through the resistance R. So in that case, the output can be written in this way, that the output voltage is nothing but the voltage across the resistance R, and which is equal to R into the current passing through this resistance. So V0 is equal to R into I with a negative sign. Why negative sign introduced here? Because the input is applied to the inverting input terminal. So from this relation, you understand that V0 is just proportional to I. So the input current is successfully converted to its equivalent voltage. So in this way, an op-amp can be employed to design a current to voltage converter. Now come to the section or topic voltage comparator. So what is a voltage comparator? It is an electronic device which compare two voltages. Okay, and here is an OPAMP can be used in this purpose, and the voltage which is to be compared is applied to the inverting input terminal, and this voltage which is to be compared to another voltage with reference to another voltage or with respect to another voltage is called the second voltage. This is VR, and this voltage is called the reference voltage. That means if you wish to compare this voltage with respect to this voltage, then this voltage will be called the reference voltage, and and op-amp can do perform as voltage comparator successfully, and you can understand easily. You will be able to understand in the further discussions. Now let us you consider that Vi, this input voltage is less than Vr. So what will happen then? And since Vr is in that case Vr will be greater than Vi, so these will dominate. So the input in the non-inverting terminal will dominate. So the output will be positive, and since the gain of an op-amp is open loop gain is infinity, so for the case when Vi is smaller than Vr, then the output will saturate to the positive saturation value, positive saturation voltage, that is V saturation. And when Vi is increases further and it when reaches equal to Vr, that means the difference will be zero. And when Vi just crosses Vr, then the output voltage will saturate to the to the negative saturation value. And viewing this voltage profile, viewing this profile, you can easily understand whether this voltage Vi is higher or lower than that of the reference voltage. And in such way you can that means when Vi is less than Vr, then the voltage output voltage is saturated to the positive saturation value, and when Vi is greater than Vr, then it will and the output voltage will switches to the negative saturation value. And so from this graph or from this profile you can easily understand whether Vi is less than or greater than Vr. And in this way these two voltages or this voltage can be compared with this voltage and op-amp in this way perform a voltage as a voltage comparator. Now another important applications of voltage comparator is there, and the comparator can be used to generate a square wave from a sinusoidal wave, and this is shown here. You in this case if you wish to generate a square wave from a sinusoidal wave, the reference voltage is made to zero. That means here the input voltage is Vi and the reference voltage is zero. So here you will understand that in when the input voltage crosses zero and it proceeds towards the positive cycle, positive values, then what will happen? Since Vi is in that case Vi will be greater than this voltage, so the output voltage will saturate to the negative saturation value. So in this part and in this part the output voltage will be remain unchanged to the negative saturation value, and whenever the input voltage once again crosses zero and increases in the negative direction, then since it will be negative direction and it is an inverting amplifier, so the output will be positive and the output voltage will saturate to the positive saturation value, and it will remain unchanged until it one again crosses the zero value. And further, in case of this cycle, the output will be in the negative saturation value. So in this way, the and a sinusoidal wave can be converted uh, to a square wave. Now come to the half-wave rectifier. You know that in case of rectifier, an AC can be converted into DC, and in case of half-wave rectifier, ordinary half-wave wave rectifier, the output will be found in case of the positive half cycles, and there will be no output in the negative half cycles. But in case of a rectifier in which an OPAMP is used, the situation becomes different, and we will see that when OPAMP is used as a half-wave rectifier, in that case the output will be found in case of the negative half cycles, but it will not be found in case of positive half cycles. That is the rectifier. That is the function of rectification of of a rectifier, half-wave rectifier using op-amp is just opposite that of the ordinary rectifier. So here is the basic diagram of a half-wave rectifier using an op-amp, and in this case the sinusoidal voltage or the AC voltage or AC signal which is to be rectified is applied to the inverting input terminal, and the non-inverting input terminal is grounded here, and two diodes, PN diodes, D1, this is D1 and this is D2, are connected in this way, and the feedback resistance is R2, and the output voltage is here V0. The output voltage is V0. And now now let us consider a sinusoidal wave or AC wave or AC signal is applied. AC voltage is applied to the inverting input terminal. Then what happens for the positive half cycle? This is the positive half cycle of the input signal and or input voltage. The positive half cycle, you know that these diode, that means diode D2, this is P and this is N side, and this is N side and this is P side. So this will be for the positive half cycle, this will be active and this will be in off condition. So D2 will be on and D1 will be off, so no current will pass through the D1, and the current will be passing through the diode D2. Now neglecting the diode resistance, the voltage across the diode will be nothing but nothing but diode resistance with a negative sign, because the input is applied in the inverting input terminal, so it is negative sign diode, and that will and the voltage across this diode will be the output voltage, and that output voltage V0 will be minus negative sign with a negative sign diode resistance by this is the input resistance, and into Vi the input voltage, and since it is taken as negligible, so V0 will be 0. Another way can be and this can be explained another way, which is that the diode D2 is connected to the virtual ground A, because and you know that this point will act as virtual ground, and since it is directly connected to this point, and then A will act as a sink, and so no current will be found in the output, and that's why the output voltage will be 0. So in case of positive half cycle, the output V0 will be 0. But in case of negative half cycle, what will happen then in that case? In that case, you easily understand that the diode D2 will be off and the diode D1 will be on. That is, it will be in operating, it will be in functioning. And in that case, no current will passing through D2, and the output that will find which will be that passing through the D1, and in this way. So in that case, if the diode resistance is taken negligible, then the output V0 will be, what will be the output? Output will be will be equal to the gain. What will be the gain? That means the net resistance acting in this region, in this connection. So that diode resistance is 0. We considered it, and it is R2. So effective resistance is R2, and in that case, the you know that the gain is equal to the feedback resistance by R1. That means R2 by R1. So the V0 will be So V0 will be R2 by R1. Why negative sign? Because it is the input voltage applied to the inverting input terminal, and Vi, another negative sign is taken here, minus Vi. Why minus Vi? Because we are considering in the negatives of cycle. So as a result, V0 will be R2 by Ri into Vi. So it will be positive, and that is shown here. So in the negative half cycle of the input voltage, no there will be a output current, and and similar way in the for the further the next negative half cycle, there will be no current, no voltage, and for the next negative half cycle there will be a voltage. So we will observe the output voltage only for the negative half cycles, but not in the positive half cycles. And in this way, op-amp can be used as half-wave rectifier. Although the rectification function of the rectification is defined that we find in case of ordinary rectifier. Now come to another important topic, which is a regenerative comparator or Schmitt trigger. What is what is it? You know from this that comparator. That means this device will compare two voltages, and regenerative means in this case positive feedback will be applied, and and we can define a Schmitt trigger as an electronic device in which a voltage switching of action will be found in case of the voltage in case of the changing of voltage from one voltage level to another voltage level. That means in this type of electronic device, or in case of in this type of comparator, uh, in this type of comparator, you will find uh, uh, that uh, switching action, and that switching action will occur when you change a voltage level and to another voltage level. And in this case, in this case there will be a hysteresis in the voltage profile, and positive, and as already and already I told that positive or regenerative feedback will be applied in this case, and an op-amp can be used to implement or to design a Schmitt or regenerative comparator. And the basic diagram is shown in this figure, and simple basic diagram is shown in this figure. And from this figure, you know that the voltage which is to be compared is applied to the inverting input terminal, and here the output, this is the output voltage, and this output voltage is feedback to the input non-inverting input terminal, and the input voltage is the voltage that is feedback to the non-inverting input terminal is Vs, and the output voltage is connected to another voltage Vr, which is by through the resistances R2 and R1 as shown in this figure. And now come to the point that the value of the what will be the value of the feedback voltage Vf. So Vf is since these two voltages these two currents these two resistances are connected in this way, so the effective and the Vf is connected in this position. So the Vf will be the Vf can be calculated from the voltage divider rule, and according to voltage divider rule, Vf will be R1. This is R1 here. The voltage drop will be R1 into V0 by R1 plus R2. And in case of R2, the voltage drop will be R2 into VR by R1 plus R2. And this can be found out by applying superposition theorem or voltage divider rule. Now, so the feedback voltage is equal to Vf, which is given by this equation. Now, if Vi is less than Vf, so in this case Vf will dominate, and the output will be due to the input that was given to the non-inverting input terminal. So the output will saturate to the positive saturation voltage, let it is say Ba. plus VA. So in that case, V0, the output V0 will be plus VA, and using this value in this equation, you will find VF is equal to R1 V0 will be replaced by VA. So R1 VA by R1 plus R2 into VR by R1 plus R2. Let this is equal to V1. Now, if you further increase VI, then the output voltage will remain unchanged, uh, uh, at VA, and when VI equals to VF, that means in this case VF was V1. So when VI equals to V1, then these two voltages will be equal, and that's why the difference voltage will be 0. And when this VI just cross VF, then the output voltage, then VI will be dominating in that case, and the output voltage V0 will switched to the negative saturation value. And if you further increase Vi in the positive direction, the output V0 will be unchanged to the negative saturation value minus Va, and in that case you can easily find out Vf from this relation also. So Vf will be there, in that case Vf will be R1 into minus Va by R1 plus R2 plus this. So that is written here. Then VF will be R2 VR by R1 plus R2 minus VA R1 by R1 plus R2. Say this is V2. So in this case, switching action of is observed in this case. Now let us be consider that the input voltage is now decreased in the opposite direction. Now after when the input voltage Vi was increased, the voltage profile was in this. In here the voltage profile is shown in this figure, and in such a way the output voltage was changed in such way, in this way. Now if you want, or if you wish to decrease the input voltage Vi, then what will happen? And then the output will remain unchanged to minus Va as long as Vi is less than V2, sorry, greater than V2, and once the input voltage Vi becomes equal to V2, then what will happen? And for the later case Bf was V2. So when Vi was decreased and it reaches to this Bf that is equal to V2, then difference voltage will be 0, and when it is decreased furthermore, then what will happen? Then this voltage will dominate, and the output voltage will saturate, or there will be the output will triggered to the positive saturation value. And how long you and if you further decrease Vi, then also Vf will dominate in that case, and the output will remain or retain in the positive saturation value plus Va. So this is the case when Vi was decreased, and if you plot these two voltage profile in the same graph, then it will be in as shown in this figure. So this voltage, let's see here. You see here, this voltage is nothing but V1, and this voltage is nothing but V2. So here hysteresis or hysteresis loss is shown here, seen here, and the hysteresis loss is obtained by the difference of this voltage and this voltage. That means the hysteresis voltage is VH is given by VH, that is equal to V1 minus V2. That is equal to 2 into, and that can be found by subtracting this relation from this relation, and you will obtain that BH is equal to B1 minus B2, that is equal to 2R1 BA by R1 plus R2. Just calculate it and you will get this relation. So in order to in order to reduce VH, you have to make R1 by R1 plus R2 small, but it cannot be reduced greatly, and if you reduce it greatly, the loop gain, that is equal to minus beta AB. AB is the gain and beta is the feedback fraction, will be very small. Now come here, in this circuit arrangement, the feedback fraction feedback factor beta was is equal to R1 by R1 plus R2, and the loop gain, we know that the loop gain is nothing but minus beta AV. So these two relations will be applied in this case. Now let us consider we wish to design a Schmitt trigger for which VR, the reference voltage VR, that means the reference voltage here, the reference voltage VR is equal to uh, 3 volt, and the hysteresis loop is 0.03 volt, and you will use an OPAMP for which the positive saturation value is 5 volt, and you have given the loop gain as V is equal to 20,000. Then you can easily calculate from this relation that VH is equal to 2R1 VA by R1 plus R2, this relation, and from this relation VH is equal to 0, and you know that R1 by R1 plus R2, that is nothing but beta, and that is equal to this. So the loop gain in this case is can be found as the relation minus beta AV. So that is equal to minus AV into R1 by R2, that is equal to 60. So in this case the gain is much higher than 1, and therefore it is acceptable, and using these parameters we can implement or design a Schmitt trigger. Now its applications, in which cases Schmitt trigger is used. An important application of the Schmitt trigger is to transform a slowly varying input voltage to a square voltage. You see here, in this case, the input voltage was slowly increased or slowly decreased. That is varied slowly, and as a result, we found a square. This is nothing but a square wave. We find a square wave when the input voltage is very slowly. And also the Schmitt trigger is a comparator. Yes, obviously it is a comparator, because it compares these voltage, the input voltage Vi with respect to this voltage or this voltage. So it is a comparator, and because the circuit compares an input voltage with the trigger levels V1 and V2 for the output voltage to switch between minus Va and plus Va. It is a regenerative comparator because in this case positive feedback was used. So I think that you will understand, you have understood, or you have to better understand, you have to study furthermore, and